Welcome to Drain Water Heat Recovery. In today's training, we'll learn about these simple but effective devices that have the potential to offer serious savings on your water heating energy. So why are we talking about drain water heat recovery? So water heating represents a significant energy load, and drain water heat recovery gives us a way to recapture some of the energy from the hot water that's going down the drain. So if we're using water at the same time that it's going down the drain, so water is coming into the water heater and water is going down the drain at the same time, these devices give us a way to recover 40 to 60% of the hot water that's used for things like showering. Um, Hot water is one of the largest energy loads in single family homes and in multifamily homes. I'm going to break that down to you and show you what kind of slice of the pie hot water represents. But there's a lot of energy there, and recovering 40 to 60% of that energy can really make a big deal. Drain water heat recovery can improve the capacity of a water heater. So maybe if we're replacing a water heater and we add drain water heat recovery at the same time, we don't need to put in such a large water heater. A quick overview of the drain water heat recovery device. These things have no moving parts. They don't require us to do anything after we install them. There's no maintenance or upkeep. We don't have to go in there and clean them out. They're non-fouling because the ones that are installed vertically, the way the water runs down them, they stay good. They're made out of 100% copper, so they don't corrode or fall apart on us. Installation's pretty straightforward, not a big deal. Of course, on some sites, it will be more tricky depending on the layout of the drains. It's a proven technology. It's been around a long time and it's got a great track record. Why are we going after the water heating energy? Well, the little pie charts here describe how water heating is about 21.7% of the average household energy use. The big one being space heating, coming in at something less than 60%. Let me find my little laser pointer here so you guys can follow along. And of this roughly 22% of household energy use, we can see that, a big piece of that is used for showering. About 60% of it is used for showering, meaning about between 10 and 15% of household energy use is used for showering. And as homes become more energy efficient, water heating becomes a bigger piece of that pie chart. So if we're doing a good job at building energy efficient homes and the space heating is being reduced, um, if we're not also addressing the water heating just becomes a bigger piece of that pie, which makes even more sense to go after the energy used that's going down the drain. Let's take a look at this chart showing end use energy by housing type. One of the things we see here is it's about 20% for all homes combined. For single family detached, we're looking at about 17% for water heating. And look here, as we go into apartments or smaller dwelling units, this becomes a much bigger percentage of the load. And in fact, in like a net zero or high performance home, it can be the single biggest load. Here we're seeing it as the single biggest load in an apartment. It really makes sense to go after this hot water energy use. Let's talk about water heaters for a second or two. Many of the standard gas and electric water heaters are pretty much the same as they were 30 or 40 years ago. This one on the right, this antique hot stream water heater was sort of the original, on-demand water heater where like when you wanted hot water, you went in and lit that gas burner and made some hot water. Um, there's been some breakthrough equipment over the years, tankless or on-demand water heaters. Heat pump water heaters are certainly much more efficient. They're my pick of the choice these days. But there's a lot of these older systems still in place. And it's important that we remember that water heater is important, but it's not the whole water heating system. Let's talk about energy savings with drain water heat recovery. We know that showering can be like 60% of the hot water use, and We can reclaim about 50% of that energy, and energy savings are about 35%. And we know that not only that, but it'll increase the water heater capacity, which means if we're buying a new water heater, we can buy a smaller one that might save us some money there. The other thing worth noting is that if we're combining a drain water heat recovery system with a heat pump water heater, the heat pump water heater will run less, which means it'll have less of a cooling effect on a home in the wintertime, and it'll make less noise. So there are a couple of non-energy benefits that are worth looking into. If we look at this infrared image here, we can see that this color going from green to red is shows the temperature of the water in that outer coil that's wrapped around the drain pipe. So as that water comes in really cold, it's blue down here. We can see it warming up. In the middle, it's sort of green, yellow, then it's red at the top. So this is great. You know, they got the range on their thermography just right to really show this at its max effect. Okay, let's talk about how these things work. When drain water is going down a vertical pipe, gravity following film forms on the inside wall of the pipe due to surface tension. And this is like a thin, turbulent film of water. It does a great job transferring heat from the drain water to the drain pipe. And incoming cold water line is wrapped around the outside of the drain pipe, and the heat from the drain water is transferred to the drain pipe and then to the incoming cold water. The drain water heat recovery device is made entirely of copper, which is an excellent heat conductor and allows efficient transfer of heat from the drain water to the cold water line feeding the water heater. So we're raising the incoming cold water temperatures that feed the water heater from 50-degree well or street water to something like 74 degrees. And that is going to depend on how fast we're pushing water through the heat exchanger and what the temperature of the drain water is. This gravity falling film allows the entire surface of the drain pipe, because it's swirling down the inside surface of that pipe, it allows the entire surface of the drain pipe to transfer heat to the incoming water pipe that's wrapped around the outside of it. It's a very effective way to reclaim the energy. Let's talk about the installation of a drain water heat recovery system. It's a vertical installation, so we're going to need a minimum of probably like 4 vertical feet of drain pipe that doesn't have other stuff branching into the main vertical riser there. So this is typically done in the basement, but it doesn't need to be in the basement. It could be in a closet or in a wall on the first floor, capturing drain water from second floor showers. It should serve at least one shower, and hopefully that's the primary shower. So the better savings are going to be by capturing more of the shower drain water as opposed to less of it. So you wouldn't make sense maybe to put one on a guest bathroom. You probably want to get it on the master bathroom, and then also a second or third bathroom if you can get the plumbing all to drain into the same vertical stack. It's pretty simple. You just cut out a piece of the old drain line and you install this thing here. So you cut the pipe here, you cut the pipe here. This is the new drain water heat recovery device that gets installed in place of the old drain pipe. Is a Fernco style fitting on the top and the bottom. You attach the cold water here. It comes in, it gets warmed up by the drain water going down the pipe, and then the tempered water comes out the top here. Let's talk about equal flow plumbing, the best insulation method. So equal flow plumbing is by far the most energy efficient way to install a drain water heat recovery system. And what that means is simply that you've got equal flow going through both sides of the heat exchanger. So if, for example, we've got 2 gallons per minute going down the drain, that means we're going to want to have 2 gallons per minute moving through the heat exchanger. Oh, my mouse just jumped on me. 2 gallons a minute moving through the heat exchanger and heading to the water heater. Before we get to the water heater, in order to make these two streams equal, we're going to have to tee off and head to the cold side of the shower mixer. Remember, showering is the big thing we're trying to capture with a drain water heat recovery system. And anything that doesn't involve going to the cold start of the shower mixer is considered unequal flow. And that means that we're going to give up some efficiency. One manufacturer claims that it's 23% less efficient to do unequal flow plumbing. In this case, this diagram shows unequal flow as simply coming off the tempered water side of the heat exchanger and straight into the water heater. In this case, not teeing off to the cold side of the shower mixer. If you look at the manufacturer's listed efficiency for their drain water heat recovery units, those efficiencies were given testing with equal flow plumbing. So if you're not doing equal flow plumbing, you're not getting the listed efficiency of the unit. Here's another way to do unequal flow piping. In this case, the piping just goes straight to the cold side of the shower mixer and not to the water heater. We can see here, coming off the heat exchanger and right up to the shower, not going to the water heater. This is sometimes done in a case where the drain water heat recovery unit is going to be installed closer to the shower and farther away from the water heater. Or it's just, yeah, it's not practical to get back to the water heater or not possible to get back to the water heater. Again, still not the most efficient setup, but better than nothing. Let's talk about the listed efficiency. When you look at a manufacturer's data chart like this one here, let me get my pointer, you'll see that the efficiency goes up with respect to the vertical length of the drain water heat recovery device. So in this case, these are all 3-inch diameter, so R3 and then 2430. This is the length here. All of these devices are primarily made in Canada. There's a couple US manufacturers, but the standard, the Canadian standard B55-1 for testing the efficiency uses equal flow plumbing. So again, if you're not using equal flow plumbing, you're not going to get these efficiencies. It is building code in Manitoba and Ontario that you use a drain water heat recovery device of at least 42% efficient. In this case, so for this manufacturer, that means you'd want to put in a 42-inch one. So at 42 inches, we're testing out at 42.9% efficiency. Here's the sweet spot inside this pink box here. So the length here between 42 and 72 inches, we start getting much over 72 inches and we have to buy a lot of copper. So the units get really expensive. And although they get more efficient, they get more expensive. And also with the long ones, you can see the pressure drop increasing here, and you can see the length of them getting really long. And it's just hard to find a place to put them in. So most of the ones we see are going in at about this length here. Here are a couple of the major manufacturers' products. The PowerPipe on the left, and the EcoDrain on the right. Now, PowerPipe makes drain water heat recovery units the old-fashioned way. They use a lot of copper. And EcoDrain uses less copper and claims improved efficiency for equal length of heat exchanger. EcoDrain is believed to be only available in the code minimum 39-inch 43% efficiency. Although they advertise other sizes, I've been seeing them having trouble expanding their other product lines into the market. EcoDrain does make a couple of horizontal options. This one on the left here, the A1000, is a 2-inch gray water heat recovery system, and it's got a D-shaped pipe, so the pipe is flat on the bottom. Hang on, this program has a little pen on it. Let's see if I can. So the bottom of the pipe is flat, and then the top of the pipe is round like this, and that's what it looks like in profile. So the heat exchanger is down here on the bottom, and they flattened it out to get a little more effective area where they're coming in contact with the incoming cold water. The B1000 on the right is it's a drain line replacement. So this uses a 3-inch main drain line, and again, because we have less surface area in contact with the vertical, the water flows down and it comes in contact. That gravity falling film holds it in contact with the whole pipe. With these, the water is just floating down the middle of the pipe here. So you just have a little bit of contact at the bottom of the pipe. So to get the same efficiency with a horizontal unit as you would with a vertical unit, you're going to need to go longer. So you have to buy a longer one and have a longer place to put it. I mentioned earlier about cost and efficiency of the units. On these ones, we can see some pricing for a couple different manufacturers versus the efficiency. What we notice is, again, like I said, the longer you go, the more expensive they get and the more efficient they get. These ones on the bottom are EcoDrain, and I got this pricing directly from EcoDrain a couple of years ago. I don't know, these units, these longer units don't appear to still be available. I don't know what the pricing is these days, and this was a couple of years ago. But back then, it was a pretty good bang for the buck. So for $375, you could get into a 43.5% efficient unit versus the 36-inch PowerPipe coming in at $564. This is recent pricing I got off the web on a Home Depot site. These are available at Home Depot, or you can order them directly from the manufacturer. The middle column represents the pressure lost. So you can see the longer one starting to creep up and give us a little bit of pressure loss. That 2.9 psi is not super significant, but for somebody who's got very marginal pressure already, I think that is something worth looking at. These next couple slides, I'm going to show you a case study, a residential case study. In this case, it started with a water heater replacement, and remember, this was a replacing an electric water heater with a heat pump water heater. They elected to only go with a 55-gallon heat pump water heater, which was replacing a 50-gallon electric water heater. Many people would have wanted to upsize this heat pump water heater so that it would have better recovery efficiency. In this case, because they were installing the drain water heat recovery, they elected to go with a 50-gallon heat pump water heater. The duct here that you see is ducting the cold air off the backside of this heat pump and putting it outdoors. Here's another look at that water heater replacement. In this case, we're looking at the exhaust duct coming off the backside of this heat pump water heater. What they've got here is two different modes. The cap off the end of the T is considered summer mode, where they can take advantage of the cool dehumidified air coming off the water heater. And in the wintertime, they put a cap on it and push that air outdoors. And it has the effect of creating a slight negative pressure in this room, which actually draws warm air from the house into this room to feed this water heater. Here is the drain water heat recovery unit. On the left, you can see it before it was installed. It's leaning up against the wall. It's very hard to tell in this photo, but this black line here is the ABS plastic vertical drain that they're going to be replacing with this drain water heat recovery device. And on the right, you can see here the Fernco fittings at the top and the bottom. Here's the heat exchanger plumbed into place, cold water feed here, tempered water is here. Here's another look at it. And you can see this, they put in a drain cock here, cold water feed in here at the bottom, and a little bit better view of the tempered water takeoff at the top of the unit. This was not the simplest, as you can see, installation, because you can see it was in a wall for one thing, and they had already demoed the face of this wall. But they also wanted to capture another shower, and they ran the drain line from the other shower. They tapped into it back here and ran a new line along this corner where they're going to build a soffit over it. And they got the kitchen sink drain to tie into it here and brought it over. And you can see on the right, it comes over up here in the corner, feeds in through the ceiling of this closet, and then dumps into the top of the drain line here and comes down through the drain water heat recovery system. So they have managed to get 2 showers and a kitchen sink onto this. Here's how they managed to do the equal flow plumbing. So here is the tempered water coming off of the water heater. I think it comes this way, and then they teed off here to this cold water feed line right here. And that cold water feed line, you can see, I don't know, here it says second floor bathroom cold. So this is the cold water line that feeds the second floor bathroom. They teed into this here. They did it again for the first floor bathroom. So instead of going to the shower mixer, which would have involved demoing the walls behind the showers, they just fed the whole bathroom. And in reality, I suppose if somebody was in the shower and somebody else came into the bathroom and wanted a glass of cold water out of the tap, they might have gotten something like 70-degree water out of the tap. But that's really the only downside to doing this. Here's a little thermography I did at the kitchen sink on this setup. Here on the left is the actual photo, and on the right is the identical infrared image. And I think what we're seeing here is we're getting like about 117 degrees at the tap on the tap water. Here is the drain water heat recovery inlet. Photo on the left is a real-time photo showing the cold water line from the well uh, going through the heat exchanger, and it's coming in. Here's the thermal image on the right showing us that the water is coming in at something like 49 degrees Fahrenheit. Pretty standard for well water in Vermont. Here's some thermal imaging of the outlet for the drain water heat recovery unit. So here we've come up in the top of the outlet, the tempered water is coming out here. And the thermal image on the right, it's a little tricky to see, but this is the tempered water line. Here's the cold water feed coming in, and here's the tempered water going out at 71.8, so almost 72 degrees. So we're coming in at 49, we're going out at 72. And here's the water heater inlet on the left. We can see the cold water feed to the water heater. On the right is the thermal image. That's coming in at 66.5 degrees. And what does that tell you? That says to me that we lost 5 degrees from the top of the heat exchanger before we got to the water heater. We lost 5 degrees to the laundry room through the walls of this pipe. So that tells me we should have insulated that pipe to hang on to that heat, because 5 degrees is pretty significant when we're only talking about a 20-degree delta T. Let's look at the energy savings from this retrofit. So they replaced electric hot water heater with a heat pump water heater. They installed drain water heat recovery. We see that they lost 5 degrees of water temperature between the heat exchanger and the water heater. So that could have been better. But even with that, the savings are remarkable. These people were using 119 kilowatt hours per month with their electric water heater. And that's now down to 24 kilowatt hours per month with the heat pump water heater with drain water heat recovery. They have had no problems running out. This is a family of 4. They've had no problems running out of hot water with their heat pump water heater, and they keep it in heat pump only mode. So at no time has it failed to keep up with that, and that's due to the increased capacity of the drain water heat recovery system. There are commercial applications for drain water heat recovery. In this case, we're looking at all of these are, I believe they're 6-inch drain water heat recovery units. They may be 5 or 6-inch diameter units. They're manifolded together. You can see the manifolds up here. Again, the picture on the right, you can see the main drain line teeing off to 2 separate manifolds. So one line being split into 4 lines going through 4 different heat exchangers. This is something like a college dorm or a hotel. Great applications for commercial use of drain water heat recovery. Here are some more larger commercial systems. The one on the left, they've done a beautiful job with the manifolds and the pipe insulation. So all of these heat recovery units were all insulated. In fact, and they've got gauges on them so they can measure the temperatures and the valves and everything. It's a great job here. On the right, another system where they've manifolded. These look more like 4-inch, standard 4-inch units. Here's a case study for the dormitories at the University of Chicago. This was given to me by Rod Buchalter from Renewability, and they make the PowerPipe. And we can see here how they've got a PowerPipe below each floor. So here's the drain water heat recovery unit here, capturing the dorm bathrooms on this floor. And then this one captures the dorm bathrooms from the floor above it and so forth. They put 46 units in this place, and they did it in something like a 7-year payback scenario, saving over $10,000 a year. Here is a hotel laundry job at a Holiday Inn. So this is an open trench. So they're dumping the hot drain water um, in this open trench, and these are fully immersed in the trench. So they have 3 coil heat exchangers. They're averaging a 27-degree temperature rise, which is awesome. This one was a 3.5-year payback. You can imagine how much hot water a hotel laundry is going to go through. It's a great way to capture it. Let's talk about drain water heat recovery in Vermont. The new residential building energy standards, the new Vermont Energy Code, is moving to a point system where you have to do all of this prescriptive stuff, and then you also have to get some points depending on how big your house is. If you install drain water heat recovery, you can get a point towards your code compliance. Efficiency Vermont's multifamily program is offering $300 per dwelling unit, so that's per apartment. Efficiency Vermont has a custom residential offering where we're giving 100% of the cost of the device only. The customer is going to have to pay for installing it and buying whatever piping and fittings they need, but we'll cover the cost of the drain water heat recovery unit. And that's typically in the $500 or $600 range. For limited time only because the next bullet point, it's in the new product development pipeline at Efficiency Vermont. So it's currently under review. We're trying to get this turned into a rebate program and trying to get the supply chain pipeline beefed up here in Vermont so that we can do that. For commercial and industrial projects, if you wanted to do a commercial installation like some of the ones I just showed you, Efficiency Vermont is here to help you on a custom basis with that. I'm sure we can provide some contacts with manufacturers who can do engineering for you, and we can help provide a cost share based on how much the savings are going to be. Vermont Gas has a $300 incentive for a drain water heat recovery unit in their territory. So if you're in Vermont Gas territory, you go to them. Here are some barriers and some challenges. Most of these are logistical. So a lot of this stuff has to do with difficulty getting access to the drain lines and the plumbing lines that we need. And that can be due to not having enough vertical drain line before the drain exits the basement heading out to the septic system. Sometimes this has to do with just proximity of um, getting your piping from here to there in a finished home can be tricky. So if it's not all easily exposed in the basement, it can be a little hard to do as a retrofit. And in fact, even if we can get at the plumbing in the basement, sometimes it's hard to do the equal flow plumbing because we can't really identify one line that branches off to a bathroom or something like that. Sometimes we can consider a horizontal drain water heat recovery system. Sometimes we can get better access than others, but for the most part, if we're considering this for new construction, there's no reason that we have to have all these barriers in our way. Like we can plan around this. We can make a smaller plumbing core where we have better proximity between the drain line and the water heater. Let me show you what that looks like. We have to look at water conservation strategies as part of the whole system. So the water heater is just one little piece of the water heating system. And we really need to be considering those other pieces of the system as well if we're going to try to maximize the efficiency of the system. Um, we identified that water heating can be one of the biggest loads in a home, if not the biggest load in the home. We also talked about how heat pump water heaters might need some mitigation strategies around their cooling and how much noise they make. And drain water heat recovery addresses both of those symptoms. It doesn't completely solve it, but it really helps. Um, water conservation and heat recovery are just as important as a high efficiency water heater. So just buying the right water heater only gets you part of the way there. I want to make a pitch to reducing the wet area or the plumbing core in a new construction whenever we can. And this has a lot to do with design. So the architects listening in on this, I hope you take note of this. This can be designed into the house for peak water heating efficiency. We're going to have to all work on it together. Here's what I mean by wet area. This is the floor plan for the HGTV smart home. And when I say the wet area, I'm referring to the area contained by all the plumbing fixtures. In this, rather sprawling layout, the wet area is a large percentage of the overall floor area. Some single-family homes can have like over 100 feet of water line between the hot water heater and the furthest fixture in the home. And this can mean like long wait times for hot water. It means gallons of water down the drain before anyone can even step into the shower. And this can add up to, I don't know, thousands of gallons per year and high energy use. And these larger wet areas can make drain water heat recovery installation a lot more expensive, or in some cases, like in the case of a retrofit, not feasible at all. And the solution would be to reduce the wet area. Here's another floor plan showing a reduced wet area. Um, Assuming the second floor bathrooms are stacked over the wet areas on the first floor. The reduced wet area combined with low flow fixtures, pipe insulation, drain water heat recovery, and a heat pump water heater makes for a much more efficient hot water system. And remember, it's a system, not a device. I'd like to thank you very much for tuning in and making it to the end. I am happy to take any of your questions. Shoot me an email or give me a call at the number here. I would like to think that you came away with an understanding that the water heating is a big part of the energy load in today's modern energy efficient houses, and that there's a lot more we can do about addressing that load than just putting an efficient water heater in place. That the water heating is done with a system and not just with a device. And that system should contain a high efficiency water heater, a drain water heat recovery system, low flow fixtures, short plumbing runs, insulated lines, the whole kit and caboodle. So hopefully I've made that point and that you're coming away with this with a better understanding of what it takes to maximize the efficiency of a water heating system. Please feel free to reach out, and thanks again for tuning in.